Okay, let's start. So there are a few announcements before we start. So first of all, the school postponed the offline class indefinitely, so we are going to take online midterm. So I promised that we are not going to have a midterm on 10th week, so we're going to have a midterm on 11th week. That's on 4th of May to 8th of May. So on these week and on 11th week, you might have a class. So other classes take a midterm during the class. So there will be 1 hour and a half midterm on Monday, which is 4th of May, and 1 hour and a half of midterm on 7th of May, Monday and Thursday. Okay, so there will be 3 problems each, total 6 problems, and each problem will assigned by 30 minutes. So it's basically the same format as quiz. So you're going to solve one problem for each of 30 minutes, and you have to submit your work by taking a photo and convert to PDF and upload to LMS. So we had 2 quizzes with this method, online quizzes, and I a little bit delayed the due because although it was 25-minute or 20-minute quizzes for each problem, I gave 5 minutes more to upload your work to LMS. But on the midterm, I'm not going to give an extra minute, so it's 30 minutes sharp. So if you're unable to upload your work within 30 minutes, there will be no grading. So you have to upload your work far ahead before the time is up. Okay. So the midterm material, let me write it down on the blackboard about the midterm. So midterm is on online, and that will be 4th of May for 1 hour and a half during the class. 5, 6, 7. On Thursday, same, 1 hour and a half, 30 minutes, 3 problems, and during the class. Okay. And okay, so another one, there is an extra homework. I think it is already up in the LMS. Let me show you the extra homework. So this is extra homework that's due on May 1st. That's due on 10th week, end of 10th week. And this is not a mandatory homework. You don't have to do it. And I'm not expecting you to get a full grade for this homework, because I'm basically asking you to write something that I didn't teach you. So you have to learn yourself, teach yourself, and learn by other sources, because although I gave a short article about what that is, but extra material can be found in the website or other textbooks. Not our textbook, other textbooks. So you have to search for yourself. And basically the question is on the bottom, that you have to answer this question, but this is not like homework questions or quiz questions. You have to write a report, comprehensive report on what this question is asking about. Basically, the article gives a standard format what I'm expecting you to write, but you have to add your thoughts about what these differential equations and singular solution is about. Okay. So this extra homework is on due May 1st of May, which is Friday, and I will give plus 20 points maximum, and you can add these points to the homework or quiz or exam score. Okay. So this point will not going to be weighted. So homework usually have 10 points for each problem, and quiz also has 10 points for each problem. So these 20 points goes to full 20 points to these homework and quiz scores, and also exam scores. Exam will be 20 points for each problem. So depending on which part you want, you can just add the component here. So you cannot split your 20 points. You cannot split these points to these three components. You have to select one of these components to add your score. Okay. So that's it. And before we start, is there any question? Okay, so let's begin. So we're going to study about system of differential equation, and we need a linearization to fully understand the system of differential equations. We will explain why, but first let's talk about linearization of one variable function and two variable functions. So first, we're talking about the one variable function, linearization of one variable function, f of x. So basically, this Lx defined by some constant plus some constant times x minus x naught is called a linear approximation of f of x at x naught. So in other words, taking a linear approximation of a function is called a linearization. Okay, and you see this is basically a tangent line. This is equation of tangent line. So this is this linear function passes through the point x naught f of x naught. So this is the y coordinate and this is x coordinate, right? And this is the slope of the graph at the point x naught. So when you have a linear function like Lx, you can approximate your actual value of function by the value of linear function. For example, here's a picture. So you have a function y equals to f of x, and here is x0 and here is y0, and here's slope. And this red line actually is a linear line, so this has a equation y equals to f of x0 plus f prime x0 x minus x0. So we're going to take this equation as L of x, give a different name than f. So although if you're looking at the global picture, then if you take x far away from x0, the value of f of x and the L of x is huge. So this is not a good approximation. But if you take a smaller and smaller picture of near this x0, in other words, if you zoom out, zoom in this picture, then you can see that this straight line is very close to the curve of this function f, and it is valid now to approximate point x near x0, the value of f and the value of L of x, right? So there's a small difference, but if x is close enough to x0, this difference is negligible. So you can safely assume that this function x, f of x, is almost equals to the value of L of x when x is close to x0. Okay, so that's the idea of linearization. Now, we were going to talk about the linearization of two variable function. So, in case of two variable function, the graph is not a line. The graph is a surface in R3. So what does linearization tells you about is basically the same thing as the one variable function. It gives approximate value, linear approximation of the value of function, but this approximation is now given by this equation, and this equation is a equation of tangent plane. Okay, so for example, if you want to set an equation of a plane inside of R3, okay, then the equation is look like z equals to, let's say, ax plus by plus c. That's the general form of a plane inside of R3, a three-dimensional space. So you see here is the constant, and here is a constant, here is the constant, and this serves, this f of x, fx serves as the coefficient of x, and fy serves as coefficient of b, and the rest of coefficients combining all these three serves as coefficient c in this general form of equation of plane. And you see, I'm only taking this part of the equation, the right hand side of the equation. So if you want to graph this equation, then you have to set z equals to L of xy. And why is this a tangent plane? So let me draw a picture of this graph. So that, I mean, you will learn this type of study in multivariable calculus in the next semester. Well, let's talk about this right now. So we have a graph of a function on, let's say, on a particular domain. So when I say this, this is the rectangular domain in xy plane where x ranges from a to b and y ranges from c to d. So when you draw this, you have to set your axis, and then on this rectangular domain, when I fix a point x comma y, then there is a value of f, let's say x naught y naught, and the value of f is given by z naught. So I'm going to take a point inside of R3, x naught, y naught, z naught, and then mark that point. And then if you combine all these points by arranging this x naught, y naught inside of this rectangular domain, you get a surface. You get a surface like here. You get a surface like this. Okay. Now, what's the meaning of a tangent plane? So basically, if I want to take a tangent plane at this point inside of this surface, then I'm taking a plane which is tangent to the surface at this point. So let's say this is my tangent plane. Okay. Let's say H. Now S. So S is given by z equals to f of y, where x, y lies in AB cross CD. And now H is given by some equation, but I want to find the equation of this tangent line. So how do we do that? So first of all, when you try to find a tangent equation of a plane, you have to find, there are many ways to find it, but you have to find a normal vector which is perpendicular to the plane. So let's say I want to take this as my normal vector, so n. Okay. So let n be a normal vector to the plane H. So how do we get the normal vector? So normal vector is combined by the cross product. Do you learn cross product in high school? Does high school teach you the cross product? 외적 배워요? 안 배워요? Okay. So let's learn now. So you have to take a cross product of two vectors, which is perpendicular to this normal vector. So let's say this one and this one is our vector, which is tangent to the plane here. Okay. How do I get two tangent vector to the surface at x naught, y naught? So one way is to just move your point x naught, y naught to the x direction and y direction. So this direction must be opposite here. So if you move your point x naught, y naught inside of xy plane, your corresponding point on the surface also moves along the surface line. Okay. However, if you move your point infinitesimally small amount by x direction and y direction, this line, this movement is almost like a vector, almost like a straight line. So I'm going to measure that. So when I move my point to this direction, this is when the x direction and this is when the y direction. So let's say CXT is x naught plus ty and cyt y naught, x naught comma y naught plus t. And then the corresponding point is now the corresponding direction is now, let's say this is dx and dy. It's a curve in three-dimensional space, so dxt is, now it follows the same x and y coordinates, so x naught plus t, y naught, and then the z coordinate is following the variable function f, so f of x naught plus t and y naught. And when I change to y direction, then it becomes x naught y naught plus t and f of x naught y naught plus t. Okay, so this is the straight line inside of the xy plane, and this is the curve inside of three-dimensional space following this curve on the surface S. I'm going to take a tangent vector of these two curves. So let's say ddt at t equals 0, because when t equals 0, that's the time when it passes through the x naught y naught of dxt is simply just taking a derivative of each coordinate. So if I take the derivative of first coordinate in terms of t, it's basically 1, because x naught, y naught are constants. So 1, and y naught is constant, so it's 0. And the important part is the last part. So I'm going to take a derivative of these functions. I don't know what this f is, but later you will learn that this differential is given by the chain rule, f of x, x naught, y naught, times the derivative of ddt of x naught plus t, and plus fy x naught y naught. So reason why I put x naught y naught is because that's when t equals to 0, and times the ddt of t equals to 0 of y naught. So this is 0 because we are taking a derivative of constant. So this disappears, and this becomes just 1, right? So basically we have 1, 0, fx, x0, y0. So this is a partial derivative of f in terms of x. So we had a vector tangent to this direction on the surface is given by the vector with coordinate 1, 0, fx, x naught, y naught. You can take a constant multiple of this vector. It's same tangent vector, but with a different length. The length is not important because we only want to find the normal vector direction. So how about the other direction? We have when we take a derivative of this function, the same thing. We have 0, 1, and in this part you just plug in your formula like in this place. Then in that case, this part disappears because this becomes x naught, and you take a derivative of constant x naught, so it becomes 0, and this part survives and derivative becomes 1. So this is fy x naught, y naught. So you have two tangent vectors. So these are tangent vectors. So this is three-dimensional vectors at x naught, y naught, z naught. So let's find out the normal vector. So normal vector is obtained by the cross product of two vectors. So when I take a cross product of 1, 0, f of x, let's abbreviate this x naught, y naught, because I don't want this expression to be too long. So I'm going to take a cross product of two three-dimensional vectors. Cross product is only defined on three-dimensional vectors. And this is defined by, this is the formula that I always remember. You take the ijk, where this I is the normal unit vector to the x direction, and j is y direction, and k is z direction. Then you plug in these entries here, 0, 1, fy. So is it familiar to you when I write this absolute value sign on 3 by 3 matrix? So this means that I'm taking a determinant of 3 by 3 matrix. So how do you take the determinant? Just take the 45 degree and minus 45 degree angle and multiply all the entries together. So you get, if I take this, this, and this, so only this part survives, right? So we get 1 times of k. And how about the opposite? So I get this part, and this part. So we get 0 and minus fyj. And here we have minus fxi. So this is simply a vector combination. So you have 3 vectors, I, j, k. This is 3 vectors in 3-dimensional space and with a coefficient. So if you combine these 3, add 3 vectors, this is, you learned, you probably learned this in the high school, just adding how to add the 3 vectors in 3-dimensional vectors. So first of all, the first coordinate of the vector it becomes minus fx, and second coordinate is minus fy, and last coordinate is 1. Okay, so this is our normal vector. So this is not unit vector yet. It just tells you this vector is perpendicular to the tangent plane. Now, how do you find an equation of a plane which is normal to this vector? So you first find out the point where this plane passes through, z minus z naught. And then you take a dot product. You product the inner product with this. So basically, you take inner product with f of x, f of y, 1, and dot product with x minus x naught, y minus y naught, z minus z naught. That equals to 0. Then that's the equation of a plane. 요거는 배웠죠. 3차원 공간의 평면의 방정식 구할 때 법선 벡터와 요거를 내적해서 0이 되게 만들면은 이퀘이션 나온다는 건. 네. So when I take this f of x, now let's put x naught, y naught here so that we don't confuse. So x naught, so this equation is basically minus fy x naught, y naught, y minus y naught, and plus z minus z naught. So z naught is nothing but the f of x naught, y naught, right? So let me rewrite this as f naught, y naught equals to 0. So let's summarize. Let's rewrite this. So leave z on the left-hand side and move everything to the right-hand side. So first we have f of x naught, y naught, and then f of x, x naught, y naught, x minus x naught, and fy, x naught, y naught, and y minus y naught. So this is the equation of tangent plane. And this part is the linearization of a surface. So what that means is I'm going to take a value on the tangent plane and approximate the actual value of the function. So if you zoom in here around the x naught, y naught, z naught, what happens is you have a tangent plane, and here is the small, so here, let's say, here figure. So here is an actual graph of two variable functions, and this is a graph of linear approximation. And we have points slightly touching each other on the plane and the graph of function. So the value of function and the value of these linear approximations are equal at the x naught, y naught, and z naught. However, if you move your x naught, y naught to slightly away from this x naught, y naught, then the value of function of L and F are different. But the difference becomes small if your displacement from x naught, y naught is very small. If you just move your point x naught, y slightly away from x naught, y naught, the difference is almost negligible. So you can approximate your value of function by the linear function. And reason why we do the approximation is it's easier, much easier to compute this linear function than the given function. So this given function could be complicated formula. So we are going to take most of the case this linear approximation to solve differential equations. So that's the idea of the linear approximation. So here's another extra work. We are going to talk about this more comprehensively when we talk about the series solution. But let me briefly just tell you the fact about the function, the Taylor series function. So you might ask, we have a linear approximation, which means that we are going to approximate the value of function by a polynomial of degree 1, right? So linear means that it's a degree 1 polynomial. What about we approximate the function with a polynomial of degree k, where k is bigger than 1? The answer is this P of n approximates the value of function better than this linear map Lx. Basically, Lx is P1x. So you see there are case order derivative inside of this coefficient and also the k factorial, and this is the polynomial of finite degree. So your index k runs from 0 to n. So the maximum degree of this polynomial is n. And Taylor theorem, this is Taylor theorem, tells you that the difference between the actual value of function and the approximation is given by this formula, where this zeta is not known. So, but it tells you that there is some zeta such that the error term, so error value is defined in this way. So you might, the important part of the theorem is that not the formula itself, but this part. So this part is important. So it says the error term is proportional to x minus x naught to the power of n plus 1, right? So it means that if my x is very close to x0, so that x minus x0 is less than 1 or much less than 1, almost equals to 0, then because of this n plus 1 power of this value, this will always goes to 0 as n goes to infinity. So it means that if I increase the degree of polynomial, of this Pn polynomial, then the value of function f and the value of the polynomial are almost equal. So as n goes to infinity, this value of f of x goes to, so opposite. So this value of Pn goes to f of x. Not only for x equals to x naught, for near x0. So not always equals to the point x0. Whenever x is near x naught, your polynomial always converges to f of x. Okay, so what happens if I move my n to infinity? So that's the Taylor series. So let me finish off by taking a remark here. So we have a polynomial called a Taylor polynomial, Pn, and given by k from 0 to n of f to the order k factorial x minus x naught k. And as n goes to infinity, it's no longer a polynomial because the degree goes to infinite, but now it becomes a series, where infinite series where k from 0 to infinity of f of k, x naught k, and x minus x0 k. I will explain what that means. When I take an infinite sum, it means that I'm looking at the limit of finite sums. However, let's suppose that we are going to take an infinite sum of these terms and suppose that these terms converge to some value. Then it says, the Taylor theorem says, this is equals to f of x, because this is almost equals to f of x near x0. So when I take n goes to infinity, the error term goes to 0. Therefore, this infinite series actually equals to the function value of function f of x. So we're going to use this equality often in the later that's okay. So here's a remark. So not always, but almost all cases of f. So I'm just vaguely tells you that this infinite series equals to the value of f of x, but this does not happen for every function. However, the function that you know, like sine function, cosine, or exponential, or logarithm, always satisfy this equality. There are examples, a weird example, that this infinite sum is not equal to the value of function, but that's not what we want to talk about in this semester. So, however, so because there is a counterexample that this equality does not hold, so we call a function analytic if this infinite series converge to the value of functions. So if the equality holds, we call f analytic. In other words, analytic function. So basically what in the differential equation, when we solve differential equation, we're trying to find a solution which is analytic function. Okay, so we're not going to worry about when this equality does not hold. So always hold in our purpose. But if you want more mathematical rigorous, then you have to remember that there is some function that this equality does not hold. Okay, so that's that. We're going to come back to this part later. Here's a general setup here. So we have system of linear equations. So for example, we have y1, y2 as two functions in the equations, and both equations are first order differential equation. Then I can solve this differential equation numerically, or you can approximate your two variable function f1 and f2 in terms of y1 and y2, and also here y1 and y2. So so this is not equal, this is approximately equal. So in other words, if I do that, then this becomes y1 prime and y2 prime equals to some constant ay1 by2 plus c, and this is let's say alpha y1 and beta y2 plus gamma. So now you can solve this by using the matrix representation that we covered in the previous week, right? Let me give us an example here. So this is a damped pendulum. So we basically, here's a ceiling, and here's a baseline, and here's the object of mass m kilogram, and here is the length L pendulum. Now there are the gravitational force, and because of this gravitational force, it will oscillate, and sorry, I didn't change this. 말을 하시지. 네, 요 얘기 아까 잘 못 보셨죠? 그러니까 요 두 개를 linear approximation 해서 이렇게 쓰면은 이제 요거는 우리가 행렬로 풀 수 있잖아요. solvable by matrix. So let's look at the pendulum example. So I want to find out the trajectory of this pendulum in terms of theta, okay, or in terms of time. But the trajectory is fully determined by this angle theta. Okay, so theta is function of time. So I want to find out the differential equation of the theta in terms of t. So basically, you have a force applying to this direction, which is tangent direction to the movement, which equals to mg sine theta. So total force applying to this mass is given by the angular acceleration times the mass times the length of this pendulum, and it always acts opposite way, so we get it is equals to ml theta double prime equals to minus of mg sine theta, because you can expect that this is like restoration force. Okay, so this is a basic equation of the pendulum when there is no damping. However, if you have a damping force, damping always applies to the opposite direction of movement. So you get a minus some constant times theta prime. So the reason why we get a theta prime is that always damping applies to proportional to the velocity, and the theta prime gives to the velocity. And the reason why you have a first degree of theta prime is because of the experimental result. So you just take an experiment, and people found out that when you have a small velocity, then always the damping, because of the air resistance or friction, applies with the proportional to the first degree of the velocity. So we have a slightly different differential equation in terms of theta when there is a damping. So this is a second order differential equation, and this is not a linear equation because we have theta, sine theta instead of theta. Okay, so there is no standard method of solving this type of differential equation. However, if the movement of pendulum is very small, so suppose that you put your object on a large string, like 100-meter large string, and try to move your object on a pendulum in a small radius, okay, then your theta is only moving within small degree. Okay, so you can expect that the theta is very close to 0, then the sine theta is almost equals to theta. Why is that? So there are many ways to think about this. You can expect that this is equal to theta by L'Hopital's rule, right? Another way is using the Taylor series. So sine theta, when theta is 0, the Taylor series of sine theta is theta minus theta cube 3 factorial, theta to the 5th 5 factorial, and so on. So this is Taylor series. And when theta is very close to 0, what is the dominating term? Can you see this bottom? 잘 안 보이시는 거 아니에요? 좀 작게. Okay. Yeah, what's the dominating term among this theta and theta cube and theta fifth when theta is very close to 0? What's the dominating term? So I asked you similar question 2 weeks ago. So theta is the dominating term when theta is very small, because theta cube is very small compared to the theta, and also theta to the 5th. So you can expect that these term is almost 0 compared to theta, and this is almost equals to theta. So that's why we can approximate your sine theta using theta. Okay. 조금만 더 크게. Okay. So then let's rewrite the equation here. So I'm going to take this ml and then divide ml on the left and right hand side. So your equation is basically looks like this, or the damping case it looks like this. So this equation is now become theta double prime plus k theta equals 0 when theta is very close to 0. When I take this double inequality here, it means that theta is way less than 1, which means that it's close to 0. So it's a standard notation in mathematics or in computer science that when you trying to explain that theta is very small. So, and also in this case you have theta double prime plus c theta prime plus k theta equals to 0. You see, what's the equation? What is this equation? This is same as spring motion, right? Spring motion without damping and without extra force. And how about this one? So you have a damping spring motion without extra force. So basically, the pendulum moves infinite oscillation if there's no damping. And in this case, because if there's a damping, the oscillation happens at the beginning of the time, but oscillation stops eventually. Okay, so you can solve your non-linear equation. So basically, you have non-linear differential equation because there's a sine theta, using linear approximation to expect your movement is basically oscillation and similar to the spring motion. Okay, so any questions? So this one is the easy part. So let's look at more important examples in system of differential equation. So when you try to find equilibrium point or the stable point, this Lotka-Volterra model is the standard model, and it says so y1 is a prey and y2 is predator, and it models the change of the population of prey and predator. So first of all, this y1 prey grow. It expands its number by reproducing itself, and the number also decreases because of the predator. So predator eats prey. So with some proportional constant b, the rate of decrease of the prey depends on the product of prey and number of prey and number of predator. So the rise depends on the product of y1 and y2, because if there is more predator, then the decreasing rate will be larger, because more predator means that they will eat more prey. And also, if there is more prey, then predator will eat more. So it depends on the product of two populations. And also, in the predator case, predator also reproduce, but you see the wolf or tigers or lions, they don't reproduce much, like as much as rabbits or other small animals. So the increasing rate by reproduction of the predator is negligible, and it only reproduce depending on the prey. So if there is abundant prey, they will reproduce. And it will die off. It dies eventually, and it dies proportional to its population. So this is the equation, the system of equation, but this is not a linear equation, because we have equation term y1 and y2 here. So we're going to take on linearization of this equation to solve the approximate solution here. Let's say there are two critical points. So there are two stable points, two constant solutions. One is 0, 0. So when there is in the beginning of time, if y1 and y2 are both 0, which means that there's no population for prey and predator, then nothing happens because no one's there. Okay, so in that case, we're going to take a linearization so that we get this equation. So let me show you the process. So y1 prime equals to, forget about this. Okay. A y1 minus b y1, y2. So first part is already a linear function, so I'm not going to take a linearization here. Let's take a linearization of y1 and y2. Linearization of y1, y2. So when you take a linearization, it's important to fix the point where you're taking a linearization about. So we're going to take a linearization at 0, 0. That's the place where we're going to study. That's our point of interest. So y1, y2 is our function of two variable function. Then this L of y1, y2 is defined by f of 0. I'm just putting into the formula of linearization. And f of what? First, you take a partial derivative of y1, 0, 0, and y1 minus 0, and f of y2 of 0, and y2 minus 0. So what's f0, 0? 0. And what's f of y1? It's y2 because I'm taking a partial derivative of y1, y2 in terms of y1. So it means that you're taking y2 as if it's constant and take a derivative of y1. So it's y2. So this whole thing is y2, but I'm taking y. So f of y1 is still a two-variable function. It just simply has no term y1 appears in here, but still it's a two-variable function. So I'm taking 0, 0 on here, I get 0. y1 minus 0. And here it gets 0. y2 minus 0. And everything is 0. So 0 is a linearization. So it's just flat plane. So you get 0 as a linearization. So basically this is a y1. Okay. How about y2? So this part is k y1, y2 minus l y2. But we already did the linearization, so this is equals to minus l y2. So let me replace the original differential equation as this linear differential equation. y1 prime is ay1, y2 prime is minus ly2. So this means that y1, y2 is equals to a0, 0 minus l. So all of the proportional constant a, b, l, k are positive constants. Okay, that's why I put the negatives here. So this is our differential equation. Okay, so not exactly the differential equation given here, but this is the approximation of the given differential equation. So when you have a positive sign and negative sign on diagonal and zeros on the off diagonal, this has 0, 0 as saddle node, which means that the curve, the equation, the solution curve looks like this. So there's no meaning of negative y1 and y2, so you don't have to worry about other quadrant. So in the first quadrant, it always moves like this. So 0 is a stable point, but it doesn't have any meaning. So whenever you have slightly away from 0, 0, so then it always moves in this direction or other direction, depending on which coordinates are which. Let's look at the next one. So let's see this one. So in this case, now you can take another critical point, L over K and A over B. How you get this linearization is find out the constant solutions just setting these two equations equals to 0. So for example, if you take a minus, so this is the y prime part, y1 prime equals to a minus by2 y1, and y2 prime is equals to ky1 minus l times y2. So if you have a constant solution, then this y1 prime, y2 prime both are 0, and we have to solve these two equations, right? It simply means that these parts are 0, so you get these points as a stable solution. So when you start from L of k as y1, a over b as y2, then there is a perfect equilibrium that there's not even fluctuation, so always stable. So the predator eats exactly amount of prey equals to the reproduction of prey. Okay, and let's take a linearization of at these points. Okay. So same equation, but when I take a linearization, so this part is okay. How about this part? So L, let's say linearization of y1, y2 at L over k and a over b. So first of all, this L of y1, y2 equals to f of L over k, a over b, right? And then plus, so f of y, 1, L over k, a over b, and y1 minus L over k plus fy2 of L over k, a over b, and y2 minus a over b. So this is AL BK plus, now in this case this is y2, this is y2, so this is A over B of y1 minus L over k, and this is L over k times y2 minus A over B. Okay, so let's combine this. I have to erase this. So what about this part? So this part is A y1 minus B times of these AL BK plus A over B y1 minus L over K y2 A over B here. So let's combine. Okay, so here's a canceling. So A y1 here cancel out, is BB here, and this is minus AL K, okay, this part. And how about here we have plus AL over K for this term. And how about this term? So BL over K of y2. And then if you combine these two, minus A y, right? So this cancels out each other. Okay. Yeah. It's a little bit weird. So this one is this one is this one. I'm sorry. So this one, where's this one? Minus. Okay, so this one is this one. Okay. So let me just take all this separately. So we have y2 and plus of al over k. Okay, so this is first one. How about this one? So linearization is same. So I'm going to take k times of al bk plus a over b y1 l over k plus L over K of y2 minus A over B and minus Ly2. So this guy cancels out, and here AL over B, and here it's AK over B y1, and here we have AL over B, and here we have the same AL over B. Minus AL over B. Okay. So this cancels out. Okay. And then let me rewrite this. So let me rewrite this as AK over B of y1 minus L over K. So in this case, I think I made a mistake here. So minus B. So this cancels out. So this part is this, and this part is AL over K. And this part is minus. Sorry, so it's a minus. Minus of BL over KY2. This part is plus AL. So this is now equals to BL over K of Y2 and minus of A over B. Okay. Now it's okay. So we know that the L over K comma A over B is the stable point. So there is something going on around that point. So let's shift your point, shift your L over K comma A over B to the origin 0, 0. So let me write this y1 tilde as y1 minus A over B and y2 tilde as y2 minus L over K. I'm sorry, it's opposite. L over K, A over B. So then I know that this y1 prime tilde prime is equals to y1 prime, and y2 tilde prime is equals to y2 prime. So I can rewrite, it's just a shifting, it's nothing changed, it only changed by the value, constant value. So what happens is BL over K, and this is y2 prime, and this is y2 tilde prime, and this is a K over B of y1. Now, so when you have a stable point of y1, y2 at L1K, LK, AB, then it has a stable point 0, 0 at y1 tilde and y2 tilde. So in that case, you can rewrite your linear equation. So this is a system of linear differential equation as y1 tilde prime, y2 tilde prime as minus BL over K, and this is AK over B, 0, 0, and y1 and y2. If you have this type of form of differential equation that off diagonals have opposite opposite degree, then 0, 0 is a center node. Look at the previous week slide. So in that case, you have 0, 0 is a stable, but around 0, 0, your solution curve will circle around this stable point. It could be a circle or ellipse. So what does it mean? This is almost the end of the question. So what does it mean? So combine these two facts. So here we have y1 and here you have y2. As we showed before, you can draw your two solution curves in one plane. That one axis is y1 and the other is y2. That somehow there are equations, there are situations like this, that one population grows infinitely or other population grows infinitely, or there are situations like it will circle around a stable point. So it depends on your constant and the initial point. So if you start off with small prey or large predator, it will die off. But if you start from exactly right amount of prey and predator, it will circle around, also with the right proportional constant here. So let's look at the MATLAB for now. Meanwhile, I will take any questions. So is there any questions? 질문 있어요? 오늘은 질문이 없네요. 잠시만요. 꺼졌네. 뭐 있어? 질문 없어요? So, here, so, for y1 prime is a y1 minus b2, and y2 prime is ky1 y2 minus ly2. So I'm keep doing this for solving numerical solution. So by now you have to understand this is very important also like you to do this on midterm or other form of test. So let me, I'm going to change a B, K, L and then see what happens. So let's say I'm starting from nice coefficients. So I don't want this, I don't want a weird figure here. So let me find out some nice figure, nice coefficients here. Okay, so let me take a small amount. So A is 0, 1 and B 0, 2 and K 0, 0, 1 and L is 0, 2. Okay, and let's define Ty. So f of Ty is now two variable functions. So a times y1 minus b times y1 times y2. Okay, and then k times y1 y2 minus l times y2. So again, so this part is representing y1 prime. Okay, then this one is y2 prime. So that's how I put these terms here. Okay. And Ty equals to OD45 of F linspace of, now F is of F about above here, and linspace is the range of T, let's say 0 to 10, and the initial value, let's say initially we have y1 is prey, so we have 10 and predator as 1. So you can take a unit of 1,000 or unit of 10,000. So this 10 and 1 means that does not mean that there is 10 animals and 1 animals. Okay, so it could be a large number. So okay, so let's plot this. Let's plot both of equations. So Ty1 and Ty2. Okay, so it goes to some equivalent point, but I think time is not enough. So let me increase the time. So let's say 100. Let's say 1,000. Okay. So here's a situation. So basically, predators start from 10, predators start from 1. So there are abundant prey, so predator increases, and when there is too much predator, then the prey will die off fast enough that it goes to 0. Then there is no prey to feed on, so predator also goes to 0. So when I increase this more, let's say up to 1,000, then the situation looks like it's fluctuating. I mean, it's periodic. So so let me zoom in here. So I think it's a little slow, but anyway, so when you 참네. 잠시만요. 이렇게 느려. Okay. So when after 200 unit of time, then there is almost the predator and prey dies off. But at that point, because predator does not feed on much prey, so prey also grows, and prey is the blue line. So when prey grows, then predators now strives again and then go back to the original. So this is the situation. It's fluctuating. So it goes infinitely circle of life here. So let me plot this in a different plot. So this is figure 1. And this is figure 2. I'm going to plot this 1, y2 in the second figure. So here's the situation. So it's not really a circle. The reason why it's not circle, although we had a circle in the blackboard, right? So when we take a linear approximation, we take that the stable point, which is L over K, comma A over B, is the circle node, center node. But this is not really a circle because actual differential equation is not a linear equation. However, the behavior is similar. So in this case, the equilibrium point is 1, 1, right? So I'm sorry, so 1, it's actually 2, 1, right? So right here, it's right here. So there is an equilibrium point, but the situation is go circle around this equilibrium point, and it doesn't converge, right? So always circle around this equilibrium point. If I start from the initial condition, which is closer to 2, 1, then the situation is a little bit different. So let me start from let's say 1, 3, right? So the predator is 1 and prey is 3. Now it's a little bit becomes more off this axis. So it does not dies off entirely, right? So it will fluctuate more more away from this 0 line. So okay. So still, the fluctuation happens at the 2, 1 here. So this is the equilibrium point. Let me mark that 2, 1 as here. Here's the stable point. It will circle around these points. Okay. Okay, so that's an example of the system of equations. Okay, so you can you can take an application to other situations like SIR model, or SIR model is already linear. So if you have another non-linear system of ODE, then you can take a linearization around the stable point and then expect that. Oh, okay, so maybe we can compare that with the linearization. So let's say let's do this. Let's compare that with result when we take a linearization. So when you take a linearization around the stable point L over K, A over B, then this equation now becomes minus B times L over K times Y2 and A times K over B times Y1. Let's compare that. So we have Y1, Y2. So here we have T instead of Y, let's say Z here, 45. But Z coordinates, we have Z here. And on the figure 2, the same thing, but with Z. So I'm not going to mark 2 points. Okay, here. Does it looks okay? So let me erase this. Let's draw it again. So Z, sorry, so this F is same. So I'm going to take a G here. Okay. All right, so here's a figure. Okay, it's hard to look. So the blue one and red are the original solution of differential equation, and this yellow one and purple are the result of linearization. So when you take a linearization, it more becomes standard situation. So these yellow and purple ones are exactly sinusoidal curve. So it circles around the stable point. Right. So this circle is on the 0, 0 because I did not take a shift. I did take a shifting. So let me shift back to the original point. So y2 is minus a over b, and here y1 is taken over L over K. Then I think it's okay. So okay, that's wait. Sorry. Y2 is A over B. Y2 is A over B. Y1 is L over K, right? A over K. Two comma one. Why is it not comes to the 2 comma 1? A B is B A over B. Y1 2 comma 1 2 comma 1. Okay, so that's it. So anyway, so this let me erase this again, redraw this. So you see the difference between actual curve and approximate value. So when you approximate, this red one is the approximate result. Sorry, so here, the red one is approximate result, and blue one is curve. So, well, this is way off from so the red one is way off from the blue one, but the approximation is valid only when your y1 and y2 are close to the stable point. So when you approximate your two variable function near L over K comma A over B, you're expecting your y1 and y2 are small variation around this L over K comma A over B. So I take a slightly larger point 3 comma 1, slightly away from this 2 comma 1. So if I take, let's say, 2.1 comma 1.1 and 2.1 1.1, then you see now it's become a little bit closer each other. So actual blue line, which is actual solution curve, and approximate solution curve is now becomes similar. Now if I take initial value more closer to the stable point, and then now becomes, well, a little bit weird. So 2 comma 1 and 3 comma 1. So when time passes away from 0, then it always diverges. I mean, these two solutions always diverge each other. But when you take a small amount of time after beginning of t equals to 0, then you see these two curves are almost equal. right? So the red curve is the approximate result, and blue one is the actual result. And these two lines are almost equal in the time t equals time near 0, right? So linearization does not always work for entire time. It only works for a small amount of time when these y1 and y2 are closer to the stable point. So it's useful when you approximate your solution near that point, but when time passes far away from the starting point, then you have to take actual solution or take a numerical solution from the original differential equation. So there are other examples of famous examples of linearizations. For example, this is what we're going to talk about on Thursday. So like van der Pol equation. So this is like a attractor and retractor. And also double pendulum. This is a very interesting question because it applies the Euler-Lagrange equations. And and in the end, in the next lecture, we're going to talk about how to solve a system of differential equation, a linear differential equation using undetermined coefficients and variation of parameter. So on Thursday, we're going to finish off solving system of differential equations, and after midterm week and the week 11 on which we're going to take a midterm, we're going to start from the power series solution, which we talk about the Taylor and Maclaurin series, and then Laplace transforms, and that will end the semester. So let me summarize again what I talked about in the beginning of class. There will be a midterm on 11th week on the class hour. Okay, so class begins at 10 a.m. So exam will begin about 10. Okay, 10 a.m. 10 minutes 10 minutes past 10 a.m. Okay, so you have to be online in order to get an instruction on how to submit your midterm. And also the format of the midterm exam is same as the quiz. There will be 30 minutes for each problem, so 1 hour and a half midterm for Monday and Thursday each. So total 6 problems will be on the midterm. You have to submit your work by taking a photo and then convert to PDF and upload to LMS. I will not give an extra hour to upload your LMS. So if you miss uploading within 30 minutes, that's it. No more extra. Or if you send your work to email, I'm not going to accept it unless there is a severe problem on server. So give plenty of time before you finish your work and then upload to LMS. And also there is extra homework during 10th week, and that's already up in the LMS. So please do that in time. It's not a mandatory homework. If you've done it, then I will give an extra credit either on homework, quiz, on exam. I'm not expecting all of you get a full score. It's a very tough homework, depending on your background, I guess. So you have to learn yourself. You teach yourself on the material that I didn't teach you. So and also you have to write a comprehensive report. So not just like homework or quiz questions. So if you're able, please do the homework. But if you're not able to do it, but you think it's important to study midterm instead of doing work to get an extra credit, then just skip it. Okay. don't bother doing the homework. Okay, so that's it. And is there any questions?